Ich darf Sie herzlich begrüßen zum ersten Benchmark hier. Wir haben umgebaut in 20 Minuten und es freut mich, dass Sie sich wieder eingefunden haben. Wir haben hier drin keine Simultanübersetzung und werden das Ganze jetzt auf Englisch machen. So, it's a great honor for me to introduce you Professor Stephen Cowley. He's the CEO of the United Kingdom Atomic Energy Authority. As a director of the Culham laboratory, he is responsible for 150 researchers, I think, and for 1,400 employees. He's also responsible for the largest fusion device on the world called JET, and we are looking very much forward to your speech. You will speak about the latest developments in the field of the nuclear fusion, and I hope you will give us also an outlook when nuclear fusion will be state-of-the-art for power plants. The floor is yours. Please, Mr. Cowley.
Thank you very much. A litre of oil. 80% of the world's fossil fuels, 80% of the world's energy comes from fossil fuels. We have, obviously, a limited amount of fossil fuels. We also have, as we've been talking about at this meeting, a big drive to cut down on the amount of fossil fuels that we use. If you look at your daily consumption, and this is the consumption of a person in the UK, you consume the equivalent of about 20 litres of gasoline, petrol, every day. It's a phenomenal consumption of energy, and it continues and it continues and it continues. In the long term, I'm a theoretical physicist, and I like putting numbers down on pieces of paper and figuring out what have we got. And in the long term, that 80% of the energy that's provided by fossil fuels can really only be supplied by three sources. There's not going to be some miracle in which we discover another source of energy, in my view, because we pretty much know the terrestrial laws of physics that apply, at the level we're at. We don't know all the laws of physics, but we do at the energies that we're at. And those three forms of energy production, this is primary energy production, that will provide most of the production of energy. Not all, because we should look for a portfolio of things, and wind and marine will play a role, are solar, nuclear energy fission with breeder technology, or fusion. Only those three technologies have the capacity, in the long run, to replace the 80% that's given by fossil fuels. Other technologies will play a role. They just won't be the predominant role in that. We know that there are difficulties with all three technologies, and they're not ready to step up right now to provide that 80%. There are different stages of that. We know that solar is playing a role already. We know nuclear fission is playing a role, but there are some difficulties with it. And certainly going to more advanced fission with breeders, requires a public consensus that's just not there at this point. And then there's this other energy, which I have to confess is sort of been the energy of the future for an awful long time. And one of the problems we have presenting this to people is that progress has been slow towards this energy. If you take a litre of seawater, so we've had a litre of oil, there's an awful lot more litres of seawater than there are litres of oil. You take a litre of seawater, there's 0.2 milligrams of lithium in seawater. It's in the salt in seawater. And there's 33 milligrams of heavy hydrogen, that's called deuterium, in seawater. And if we could do fusion energy, which I'm going to describe to you in a moment, we could get about a kilowatt hour out of 1 litre of seawater. And if we could do a more advanced form of fusion energy, we could get about 1,000 kilowatt hours out of a liter of seawater. It's phenomenal amounts of energy. You would need every day about 200 liters of water to supply your energy needs. And if you scale that to the world's energy needs, and you ask how many years could we power the planet with the easiest fusion reaction, it'd be about 30 million years. So it's a phenomenal resource, and for that reason, we're going to have to try really hard to see if we can exploit this resource and make it into a power source. Obviously, the more harder we're having enough trouble doing the first easiest fusion reaction, so the next hardest one, let's leave that for a future date. We'll just talk about the easiest one at this point. So it's with that realization, which we've known for about 50 years, that in seawater, available essentially to everybody, it's not just seawater actually, it's in pretty much every kind of water, pretty much available to everybody, we would be able to power the planet. So around about, well, in the late 80s, Gorbachev and Reagan met and they discussed what they could do together because there was so much tension that might be constructive for the world. And they started to talk about actually building the world's first real fusion reactor. And politics goes up, politics goes down, everybody's talking about this. We started to produce designs for this in the early 90s. It wasn't until around 1999, 2000, with the realization of climate change becoming a much more political reality, that a consensus had built that we, as a worldwide project, to build the first fusion reactor. And that project's gone forward, and we're actually building it now. This is a engineer's picture, CAD drawing, of what we're building. We're building it in southern France, and if you want to put an experiment anywhere, Provence is not a bad place to put it. The other option was northern Japan, which for various reasons would not have been a good choice. It's being built in southern France in a place called Cadarache, and it's to be completed around about 2020. And it's a collaboration with more than half the world's population, because it's a collaboration between the EU, which is the EU and Switzerland, which is the largest partner in it, and then the US, Russia, China, Korea, Japan, and India. We're collaborating to build this. It's going to cost more than 10 billion euros. So it's a phenomenally expensive experiment. But if it succeeds, and I'll show you that we really believe from our calculations that it will succeed, that it will demonstrate that you can generate power at the scale of a power station from fusion. It won't show that we'll make a lot of money with it yet, but it will show that we're there. We've got the science right. We're on track, because the aim is to generate more than 0.5 gigawatt of power, which is sort of the size of a smallish power station, for hundreds of seconds at a time, and now I think we believe probably thousands of seconds at a time, in pulses, with a power amplification factor of over 10. And I'll show you some actual calculations of what we expect it to do. So it's within that context. I keep getting from people, when will fusion happen? Well, actually, we've done fusion in the experiment in my lab. And when we do this experiment, we will actually be doing fusion at the scale at which you want to do fusion for a power station. It's been a long time, and it's phenomenally difficult technology. But what I always say about fusion is it's the perfect way to make energy, except one thing. It's really, really hard to do. And eventually, we'll figure out all the things that we need to know to be able to do it, and it will be the energy source of the future. The problem for people like me is to make it sooner, right? Not 100 years from now, but when we need it. We need it this century. We need it actually as soon as possible. This is the reaction. So hydrogen comes in three forms. It comes in the hydrogen that you normally think of, H, which is one proton in the nucleus. And it comes in heavy hydrogen, which is one proton and one neutron. And so in my picture, the neutrons are blue and the protons are green. That's not the color in nature. And so deuterium fuses with another kind of hydrogen, which is called tritium, which is in this picture the green and 2 blues with it, it'll fuse together to make helium plus a neutron. And when it does, it releases copious quantities of energy. And tritium doesn't exist in nature, but deuterium does. It's in seawater, 1 part in 6,000 of the hydrogen in seawater. So you have to make your tritium, and you make it by taking that neutron and allowing it to bombard lithium. And when it bombards lithium, it makes another helium plus the tritium. So the fuels for fusion are lithium and deuterium, because tritium is just the intermediary in this process. That's the process that we want to do. But it isn't very easy to do. And it's not very easy to do because you have to understand a little bit about physics here. And of course, I'm a physics professor by training, and I love to tell people about physics. So you're going to be totally bored, but anyway. There are 2 forces that dominate the way the nucleus of the atom works. One is the fact that the atom's made up of positive charges, and like charges, remember this from physics, repel. Right? And so those positive charges repel. But there's another force called the strong force, which is what grabs the particles and pulls them into the nucleus. But it only acts at a short distance. So if you fire a deuterium and tritium at each other, at not too large an energy, what you get is something like this. They bounce off each other like that. And they bounce off each other because at distance, they repel. And if you fire them a little bit faster, so that they get close enough that that strong force will grab them and pull them in and make a helium nucleus, it'll do something like this. It's a cheap laugh, actually. I'm sorry. There's no noise in fusion. What happens in that reaction is if you get them close enough, that strong force will grab them, pull it into the nucleus, and for an instant you make helium-5 with 5 particles inside there. And it splits up into ordinary helium and that neutron which fires out. And the energy is carried away by the kinetic energy, the motion of those particles coming out. And if you can make that happen many, many times, you can generate copious amounts of heat from this. Huge amounts of heat. 12 milligrams, this is a nice statistic, 12 milligrams of deuterium and tritium in a fusion reaction will make a ton of TNT. Okay. How? Now here's the problem. In order to get them together, you've got to collide them at speeds, not normal speeds for molecules or atoms moving around. And so to get them to move fast enough, you have to heat them up to immense energy so that they're running around. So you have your deuterium and tritium running around. Most of the time when they collide with each other, they'll just bounce off. But every now and again, they'll fuse. So if you can get deuterium and tritium up, as it turns out, to about 200 million degrees, then it will spontaneously start to fuse and produce energy. Now that sounds impossible. And you'll see in the press people say, well, how can you do that? Get anything up to 200 million degrees. These people in fusion are berserk. Well, we've done that. That's the bit of fusion that we've done, and we've done it in my lab, right? And the way we do it is we take deuterium and tritium, and we put it inside a big magnetic field, and we push on it with a magnetic field, and we hold it off the wall. And when we hold it off the wall of the container and heat it up, it doesn't conduct its heat to the outside. It gets hotter and hotter and hotter, and when it gets up to the temperature at which fusion happens, then you start seeing fusion come out of it. Right? But it's this magnetic bottle, the cage of magnetic field that holds the thing together that's critical. And for about 30 years, we made pathetic magnetic cages. We could not hold this wriggling, turbulent, hot plasma, as we call it, of deuterium and tritium. It was just wriggling about, and the magnetic field couldn't contain it, and we hadn't shaped the magnetic field in the right way. Sometime around 1990, we started to get success. The temperatures that we could achieve went over 100 million degrees. We started to be able to hold it steady at that kind of temperature. This is, in fact, a simulation, because now with big high-performance computers, we can simulate what's going on inside these devices. And this is a simulation of what's going on inside, what you can see is the turbulent behavior of that plasma illustrated on the computer. Because it's hot in the middle of these plasmas, it's at 200 million degrees, and at the edge, it's room temperature. And you've got this tremendous temperature gradient causing it to bubble, just like when you put your boiling water on the stove and heat it on the bottom, you get bubbling. You do in these devices too. And in 1997, up till 1997, we'd never done any significant experiments with tritium, because it's a hard substance to handle, and because we were just getting to the stage where we could make the conditions for fusion. Then in 1997, JET, which is in my lab, is the Joint European Torus. It's the world's only machine that can actually achieve fusion, did a series of shots in which it demonstrated actual fusion energy coming out. Now, what you can see along the bottom here, this is an artist's picture of JET. Along the bottom here is time. And in 1994, the American machine, which was so heavily beaten by JET, they closed it down. TFDR in 1994, the green line, they got to 10 megawatts, but only for a second. And then in 1997, JET did its historic runs with tritium in it, and you can see we hit 16 megawatts of fusion power coming out of the plasma. We were heating the plasma with just a little bit more energy, about 20 megawatts of power to get it to that temperature, but we got 16 megawatts out. And that was a pretty remarkable amount of energy, but the key thing was that we didn't really sustain it. You can see it only lasted for 2 seconds, roughly on here. But what we did do was be able to sustain for 5 seconds about 4.5 megawatts of energy coming out. And this was the model to go forward. Because, of course, you don't want to make a burst of energy. You want to make sustained energy. You want to shovel, you don't really shovel it, but shovel deuterium and tritium inside your machine, burn it, make lots of heat, and just continue to do it ad infinitum, holding it there with your magnetic fields. And we're only able on JET to run for 5 seconds at full power, because it overheats. But for 5 seconds, we were able to hold it at 4.5 megawatts of fusion power. That was the model to go forward for ITER. We knew then that we can make a device by scaling it up, by understanding our physics, that we could go further. We're going to do another series of fusion shots in a couple of years. Well, it'll probably be 2015 by the time we reach the records again. On JET, and what we think now is we'll be able to sustain the 16 megawatts or maybe even 20 megawatts on JET for the full 5 seconds. But this is just the precursor to ITER. ITER is going to produce 500 megawatts, half a gigawatt of power, and sustain it for hundreds, if not thousands of seconds. Right? If you look at this device, it's going to be a marvel of engineering. It's a huge amount of work for a European business building this device, very high-tech stuff, superconducting magnets at 4 degrees Kelvin, 4 degrees above absolute zero, right next to a plasma at 200 million degrees. It's a fantastic bit of kit. This is one of the latest computer simulations of how it will behave. And here were various different scenarios plotted out. So this is trying out different things with the machine, using calculations to see how ITER will behave. So on the bottom here is time in seconds. And you start everything with this solid blue heating. On the right-hand side, you can see megawatts of power. And the solid blue heating is what you use to heat the plasma up. You've put deuterium and tritium into your machine, and now you're heating it up. You pour in here about 70 megawatts and step it down to about 50 megawatts of power, and the temperature roars up, and you start seeing fusion power. And so the different lines are different scenarios. And so something very interesting happens here. And some of the latest calculations suggest that we might get to a very interesting state. So you go up to 400 seconds here, and you're pouring in power to keep it hot, and energy's coming out. Now look at the red scan, which of course is the most optimistic one. At the top there, it's producing over 500 megawatts of fusion power, but when we turn off the external heaters, it keeps going. And that will be the moment that we're all looking for, because then it's self-sustaining. It's burning. It's providing the heat itself to keep itself hot, and then it's pouring out 500 megawatts of power. So you don't have to put any heat in to keep it at that state. And that's the nirvana that we really want to get out of ITER. And that probably will take us several years to get to. We start ITER in 2020, we move forward to about 2025 to 2027 when this kind of activity, we hope, is online. And I'm going to spend my retirement, I think, working on that machine. So, that's not the point, of course. The point is to make electricity. That'll be a wonderful experiment, a historic experiment. It'll be the first time we've done self-sustaining fusion. We've promised for 50 years to do it. We'll do it. Right? But how do you make a power plant after that? So the EU has had a big study with a bunch of engineers to design a power plant in this way. And this power plant design, right, is something that we intend to bring on about 2040. The current plan of the European Commission, Euratom, is that in 2040, this machine will start running. This will be the first real electrical machine, producing electricity for the grid. It'll be, in a sense, a prototype, but it's the first one of that kind. A big challenge to get there by that time, right? But our competitors think they can get there 10 years earlier. The Koreans, the Chinese, and the Indians both have plans to get their first electricity probably 10 years before 2040. Right? You can see here a demo. This is the Korean plan, starts in 2030. Is it competitive? I mean, no point in producing electricity at a cost that nobody wants to pay for it. Will it be competitive? Well, you know, you can take this with a pinch of salt, because I am a fusion advocate, right? I've spent a lot of my life working on this physics. It's fascinating physics, but the engineers did a very detailed job trying to cost out what the electricity would cost from this. And the important thing, this is the combined cycle gas turbines, fission, wind costs, and you've got a lower and upper bound on the cost we're expecting. You can see fusion comes in the ballpark. If the cost, you know, when we had to build a machine of gold, it came out at, you know, 200 euros per kilowatt hour, then nobody would want to build these things, right? But the fact that it comes within the error bars of what we're doing suggests we're on the right track. And clever engineering may get us there in that kind of time scale. What about the waste? Now, in here, on the left-hand side, you're plotting something called radiotoxicity. It's a measure of the danger of the radioactive waste that you get from your device. Now, fusion doesn't produce any radioactive waste out of its reaction. But because it produces a neutron, it can activate the walls of the device. But even that activation of the walls of the device can be brought down because we've designed special steels that the wall is made of that don't get very radioactive and have very short half-lives, so they decay away very quickly. So the total amount of radioactivity on this index starts at 0 at the time of the shutdown of the device. The top lines are fission reactors. They're the modern fission reactors that are being installed in Europe. About a factor of 1,000 down at the end of the life of a fusion reactor is what you've got. And then it decays very quickly until it hits this black line at about 250 years. That black line is the radioactivity of coal. So your device is now about as radioactive as a lump of coal. So that's good. I'm at the end of the time and it's flashing red at me. You see, we did fusion on JET, and we're pretty certain, because ITER is twice the size of JET, that ITER will actually do copious amounts of fusion. It will demonstrate the scientific viability of fusion. It's not clear that we can deliver reliable and cheap electricity. And that's what we've got to work on. I mean, there's a bunch of engineering challenges here to make these things cheaply, reliably. You don't want a fusion reactor that's off 90% of the time. It's a very expensive piece of kit. We can't do fusion small, it turns out. Various physics reasons that you can't make it small. So it needs huge amounts of investment. But if you ask what market it's going into the energy market, which is about 6 trillion a year. So if you take 30% of that market, say 2 trillion, right? You've got a huge market that you're going into. So you should be willing to spend a lot of money developing this technology, right? And I hope we will. Who will run the fusion economy? I hope it's not our competitors. I hope it's us. Thank you.
Thank you, Stephen. May I ask you the first questions? Your project or R&D is very expensive, and the European Union is not in a very strong position at the moment. All the countries, the member countries, are looking for savings. Do you expect impact to your project?
There are serious cost overruns on ITER, and of course that's difficult. There are serious cost overruns on every large piece of engineering we seem to be doing these days. It just seems to be a factor in everything. Do I think there's an impact? I think that everybody realizes how serious this is. If we don't do something, and then sometime in the latter part of this century, we're going to be energy poor. We're not going to have the energy that we need to power our modern society. There's a huge number of things that come due at the end of this century. You know, we have the issue of the aging population, we have the issue of soil erosion, we have the issue of water. All these things will depend on us having cheap, available energy to solve them.
Thank you. Do you have questions? Are there questions in the audience? Please.
My name is Samuel Leopold. I'm from the local utility here in the area. My question is, we wanted to start a conventional nuclear project, and we found it tremendously difficult to find people who actually have the right university background to work in the nuclear industry. Now, I guess money is one thing, but how are you finding people who are willing to endeavor on this, given that everybody nowadays gets some money for research, plus gets credits from his family for doing studies rather in renewable energy and this kind of good technology?
It's interesting. I was just at a meeting in Princeton, where I used to work, and the head of the fusion program for India and China were there, and the Koreans. And China is training 500 PhDs a year just in fusion, let alone fission. Right? They have cash. They don't have a cash problem. Right? They have cash. They have willing young people. They have brains. They have an engineering industry. And they're saying, it's very interesting about technology development here. The reason we are delaying making a demo reactor to 2040 is risk. We might build something that wasn't quite right, so we're trying to de-risk everything and make sure that all the I's are dotted and all the T's are crossed. The Chinese are saying, we can't wait. We have this huge population and we have to provide energy for them, so we're just going to take a risk because we've got cash. So the head of the Chinese program is saying, we're only in ITER to learn from you guys what you know, because in the 20s, what we're going to do is build a reactor. Right? So they may bring a reactor online by 2030, which is only 10 years after the start of ITER. I mean, other people are very aggressive in this space.
So my name is Louise Moody. I'm from the ETH. I just have a question. Now we've heard, I'm not trying to color this black or anything, but I'm just a bit worried because we hear it's difficult, we hear it's costly, but you didn't really tell us about the risk. Can you go in? I mean, now we're going out of the nuclear because of all the risks that we don't want to take about, but if I understand well, I understand your physics, the way you kind of described it. I have the feeling this is going to be the mother of all explosion if something ever happens. So can you please explain?
The risk isn't a physical risk. We've analyzed the safety of such reactors. Now, inside ITER, you've got less than a gram of material. And so if it all fused at once, it still would not break the containment vessel. The difference is that you don't have all the fuel around. You keep it elsewhere. So the worst case accident, and this was analyzed using nuclear safety standards, which you may or may not agree with, worst case accident does not require us to evacuate the surrounding population because it's mainly a physical explosion, there is not much release of radioactivity, et cetera, et cetera. The risk we're talking about is financial risk. For instance, we don't know how materials will behave once they've sat on the wall of this device being bombarded by neutrons day in, day out for 20 years. So if your wall only lasts 2 years, you've built a very expensive device which you have to take down and rebuild the wall every 2 years. And that will be a lot of money wasted. And so it's that kind of risk that China's willing to take. China's willing to say, you know, we'll build it with one kind of wall. If we have to change the wall after 2 years, that's a little more cash, we'll do that too.
We are short in time. They are chasing me from behind. So maybe I would like to ask you the last question. What do you think personally about solar and wind energy? Do you have a solar PV installation on your roof?
Look, I do, yeah. I do. The energy problem is so serious, there is not a stone we should leave unturned. We could be in a situation in 2050, 2070, when we're seriously short of energy at a price we're willing to pay for in the European Union and in Switzerland. I keep remember that you're not part of the European Union. And so, you know, it's important to develop cheap wind. It's important to do the marine. It's important to do all the solar stuff. I believe solar is coming down in price. And it might be that they beat us to it, and we don't need fusion. Great. That would be fantastic.
Thank you very much, Stephen Cowley.